Alright, ladies and gentlemen, recording has started. So let's go through this process here and make sure we get all the things that we're supposed to get out of it, okay? First step in the process, what's the first thing we should do? Nick? Find what we're looking for. Nick, what is this question asking you for?
How many moles of sodium hydroxide?
Okay, so this question wants to know how many moles of sodium hydroxide are produced, right? Okay. Next, what do we do after that? We've determined how much, what we're looking for. Where do we go next? Eris, what do we know? So Eris, what's one thing we know from this problem?
2 moles of sodium.
Okay, we start with 2 moles of sodium. That's something we know. What else do we know? Jen? You have 3 moles of water. Oh. 2 moles of sodium, and then 3 moles of water. Okay, and we said that in the process of getting the information that we know, there's one really important thing that we need to have in order to do a stoichiometry problem. What is that one really important thing?
A balanced chemical equation.
Balanced chemical equation. Okay. These numbers right here, the 2 moles of water, or 2 moles of sodium and 3 moles of water, these are the amounts that you have. That has no bearing on the balancing of the equation. Right? Hey. These are amounts that we have. This has no bearing on the balancing of the equation. So, to get a balanced equation, first thing we need to do is we need to determine our reactants and our products. What are reactants in this class, or in this reaction? What are we starting with? Nick, go ahead. Sodium and water, right? When sodium and water react, right? When sodium and water react. So, sodium plus water, right? And then, hold on one second. All right, so balanced chemical equation. We have our reactants. We also need to know our what? We need to know the products. Andy, what are the products of this reaction?
Sodium hydroxide and a diatomic molecule of hydrogen.
To form sodium hydroxide and a diatomic molecule of hydrogen, right? So that forms sodium hydroxide plus hydrogen gas. Okay. Again, these numbers that we underlined in red, they don't mean anything to balancing this equation. So the first thing we gotta do, we gotta balance this equation, right? All right, so looking at it here, we've got sodium. Sodium looks good. Oxygen looks good. Hydrogen, not so good, right? We got 3 hydrogens in the products, but only 2 hydrogens in the reactants, right? So I threw a 2 out in front here, right? Because that takes my sodium from 3 to 4 over here on the right-hand side. Okay, yes? We've got to count up both of them, all the sodium, or not sodium, hydrogen, my bad. Okay. We got 4 hydrogens over here in the products now, okay? So that's going to require that I throw a 2 out in front here, and that makes my hydrogen balance. Oxygen, that takes my oxygen from 1 to 2. Oxygen 1 to 2, right? But then throwing that coefficient out in front doubles my sodium, so I've got to double my sodium here. Okay? Good there? If you need to do the formulas underneath the arrow and do the atom counting, fine, do it that way. As long as you can balance the equation, that's all we need. Okay? All right, now we have to make a decision. We know that we have 2 moles of sodium and 3 moles of water. Which one should we use to start this problem? Should we use the sodium or should we use the water? Sodium. Okay. Zia, do you want to tell us why, or is it just a wild guess?
Yes, I said because in the problem it is mostly 2s.
Okay, so if we look at the coefficients, right, the ratio between sodium and sodium hydroxide is 2 to 2, and the ratio between water and sodium hydroxide is 2 to 2, right? So we need just as much water as we do sodium to make this reaction go. Which one do we have more of? Water. So which one's going to run out first? The sodium is going to run out before the water runs out, right? So that's why when we go and do this conversion, we're going to start with this 2 moles of sodium. Okay? Then, time sign, fraction bar. What unit has to go on the bottom?
Moles of sodium.
Moles of sodium has to go on the bottom, right? And then what's going to go on the top?
Moles of sodium hydroxide.
Moles of sodium hydroxide, because that's what we're looking for, right? Is this okay to have 2 different formulas in the same conversion factor? As long as what's in front of them? As long as we're dealing with what unit? The same unit. No, not the same unit. It's got to be moles. We'll see why it's not the same unit in a second, okay? So then, Jeremy, that means that this here becomes our what?
Mole ratio.
This is our mole ratio, right? And Jeremy, where do the numbers in our mole ratio come from?
The formula. Or the coefficients of the formula.
2 there, 2 there, right? So that makes this pretty easy then, and we end up with 2 moles of sodium hydroxide. Are we good with the process? I would expect you to be able to do everything up until the star, okay? I'm not gonna make you decide which one you use, all right? But determining what's in there, getting the equation, especially for this, if I gave you all of the formulas, I expect you to be able to pick out what are the reactants, what are the products, that kind of stuff, okay? Andy, go ahead.
When it says 2 moles of sodium hydroxide at the end,
Yep.
what does that represent?
Well, you tell me, what does that represent? Because what were we looking for? The first thing we talked about was what do we need to know in this problem, right? What are we trying to find?
How much sodium hydroxide is produced?
How much sodium hydroxide is produced, right? So this number right here is going to represent what, Andy?
How much is produced?
That means that's how much is there when?
After the reaction?
After the reaction occurs, we're going to have 2 moles of sodium hydroxide left. Okay? Can you tell me what else we'll have? If we put 2 moles of sodium and 3 moles of water in a container and said go react, there will be 2 moles of sodium hydroxide in that container. There'll also be a couple other things. Discuss with the person next to you what other things will be in that container. Go.
Since you didn't figure out the mole ratio for water, wouldn't that not be the answer of putting the 2 elements, or putting 2 moles of sodium in 3 moles of water?
That's what we're good at. Okay. All right. So let's discuss. If we put 2 moles of sodium and 3 moles of water in a container and said, hey, go react, there will be 3 things left in the container at the end. One of those things will be 2 moles of sodium hydroxide. What else will be in the container? Andy?
Hydrogen gas.
How much?
1 mole.
1 mole of hydrogen gas will also be in that container. Okay. What else? Jonathan?
1 mole of water.
1 mole of water will be in that container. Because, right, we reacted 2 moles of sodium, right? But, Jonathan, how many moles of water do we need to react with that 2 moles of sodium? 2, but we got 3 moles of water, so there will still be 1 mole of water left over because we didn't use all of it before our sodium ran out. Okay? That good? Nick, go ahead.
If we start with 5 moles, how do we end up with 4?
Because it's those, okay, Nick, going back to balancing equations, right? The idea behind balancing equations is conservation of mass, right? Okay. Moles don't deal with mass, they deal with what? The the number of things. Does that make sense?
Yeah.
Because each of those atoms weighs differently, we don't necessarily have to have the same number of stuff. The mass has to match up. Okay? Does that make sense? And if, Nick, if we went here, right, if we looked, if there's 2 moles of sodium atoms, if we look at all of our products, right, 2 moles of sodium hydroxide, that accounts for the 2 sodiums, right? Does that make sense? And then here, there's 2 moles of oxygen included in that 2 moles of sodium hydroxide, yes? And 1 mole of oxygen there, right? So that takes care of this, okay? Yes? Are you following me? Yeah. And then 2 moles here, 2 moles here, right? But that's only really half a mole because it's, does that make sense? Okay. I lost you on that last one, but it's okay. It's the mass. It's not necessarily the number that has to be the same. Does that make sense? Are you okay with that? Yeah. Oh, duh. That's why. Not all of it reacted, right? Does that make sense? So yeah, if we see with that, because some of it got rearranged, but some of it didn't. So we might see a difference in the total number of moles, but the mass is going to still be the same. All right, good there? That's a tough one, but definitely still where we're going. Okay. All right, next, on your outline, on Wednesday, we talked about Roman numeral number 2, which is our mole calculations. That's the basis of all of our stoichiometry problems dealing with the mole ratio. On Thursday, we moved to the back and we did mass mole calculations, where we had to make use of the formula mass to get our reactant in a unit that is convenient for comparing it to other parts of that reaction. Today, we go mass. And mass starts with this problem. All right. So it says, tin 2 fluoride is added to toothpaste to help prevent cavities. You don't have to worry about the Roman numeral number 2. That's something they'll learn in chemistry. Okay? It is made by the single replacement reaction of tin with gaseous hydrogen monofluoride. How many grams of tin 2 fluoride are produced from 30 grams of hydrogen monofluoride? So, let's go through this step by step, right? First thing we should do. What's the first thing we should do? What are we looking for, Sam?
Tin 2 fluoride, grams of tin 2.
How many grams of tin 2 fluoride are produced, right? So, how many grams of SnF2? Okay. Next. Where do we go next? We know what we're looking for. What should we do next?
What we know.
What do we know, Andy?
We know that tin's made with a reaction of hydrogen monofluoride.
Okay, so go ahead.
And it creates tin.
Okay, so one of the things that we need to know is a balanced equation, right? That's one of the things. We can do that first, right? So let's start with our balanced equation. We have to know reactants and products. So what are the reactants for this reaction? What are the reactants of this reaction? Say it again. Tin and gaseous hydrogen monofluoride. Okay? So we're going to start with tin. That's the symbol for tin. Plus HF. That's the symbol for gaseous hydrogen monofluoride. Okay. And it says it is produced by a single replacement reaction. Right? I will not make you do this on the quiz. Okay, but tin is a metal. hydrogen, even though it's not really a metal, it's more metal than fluorine is, okay? So, and you know that in the end, the tin has to join together with the fluoride, right? So this has to be one of our products, and that means that the other product is going to have to be what? Diatomic hydrogen. Love that we're like using proper terms too. Diatomic hydrogen. All right, so are we balanced? Nope, but it's pretty easy to balance, right? Throw that out front there, and then we're balanced. Okay. Yes, no, maybe. Andy, go ahead.
Where did the hydrogen come from?
Okay. Single replacement reaction, right, means that we start with an element and a compound, and then that element goes in and kicks out part of that compound and forms its own compound and leaves the other part by itself. Okay? That's single replacement reaction.
Okay.
Element, compound, element, compound.
All right.
Okay? All right. One more thing we know. One other piece of information that they gave us to work with in this problem. What else? Andy, go ahead.
30 grams of hydrogen monofluoride.
30 grams of hydrogen monofluoride. Okay. All right. So we figured out what we're looking for. We figured out what we know. And we have our balanced equation. Here we go. All right. So we start off with what we know, right? Time sign, fraction bar. What unit has to go on the bottom of this conversion factor? Grams of hydrogen monofluoride has to go on the bottom of that conversion factor. All right? Now, we might be tempted to do this. Right? Because that's what we're looking for, yes? But what's the problem there? Why can't I do that?
That's not one of the ratios.
It's not one of the ratios, right? The ratio that we're concerned with most often in a stoichiometry problem is what, Eris? The what? The what ratio? The mole ratio. Can I compare grams of one thing to grams of something else? If I have 10 grams of something and 10 grams of something else, is that the same number of things? It's not. These ratios up here, the coefficients of the equation, give us ratio of moles. They don't give us ratio of grams. I can't say that 1 gram of tin reacts with 2 grams of hydrogen monofluoride. Doesn't work that way because those atoms weigh different amounts. We need to compare the number of things, not the weight of things. So you can't go straight from grams to grams. As it shows you on your outline, right? Look, road closed. No direct route from grams of A to grams of B. It doesn't get any more subtle than that, right? It's like, yeah. Right? So, we can't go directly from grams of one thing to grams of something else because grams is not a unit that we can compare one to the other, right? So, what unit's going to have to go on the top of this conversion factor? Andy, go ahead.
Moles of hydrogen monofluoride.
Okay. That's all right. We can go grams of one thing to moles of something of that same thing. When we put in numbers into this conversion factor, if we're going grams of this to moles of that same thing, what number goes in front of moles? 1. Even though there is a 2 coefficient in front of that compound in the equation, when we're converting grams of something to moles of that same thing, we always do it on a 1 mole basis. What number goes in the bottom of this conversion factor?
The average atomic mass of hydrogen
Except now it's not the average atomic mass, it's the what? It's the molar mass. And we said that yesterday we also sometimes call that the what? We were talking about the molar mass for a compound. We said we also sometimes call it the formula mass, all right? So unless I'm mistaken, this should be 20-ish,
Yeah.
20.01, is that what it is? Again, sad that I can just do that off the top of my head. All right, so we got that. Mathematically, grams cancels here, right? And the unit we're left with is moles of hydrogen fluoride. But that's not the unit that we want, right? So, where do we go next? Time sign, fraction bar. What unit has to go on the bottom of this conversion factor? Moles of HF have to go on the bottom of that conversion factor, right? Because that's got to cancel. And then, what's going to go on the top? Moles of tin 2 fluoride. Moles of one thing, moles of another thing. That's okay. That means this is our mole ratio. Right? You don't have to label it every time you do the problem, but you can if you want to. Okay? Where do the numbers in the mole ratio come from?
Can't remember the name of them. The numbers in front of the chemical equation.
The coefficients, right? So what goes up here? What goes on the top of this conversion factor? 1 on the top, and then 2 on the bottom. Moles of HF, those are going to cancel, and we'll be left with moles of tin 2 fluoride. But that's not what the problem asked us for, right? Time sign, fraction bar. What unit has to go on the bottom of this conversion factor? Moles of tin 2 fluoride has to go on the bottom. And then what's go on the top of this conversion factor? Grams of tin 2 fluoride. Again, this is okay. We can convert moles of something to grams of that same thing. When we do, what goes in front of moles? 1. Regardless of what the coefficient is in the equation. In this case, it's 1, but even if it wasn't, that number is still 1. Because when we compare moles of something to grams of that same thing, it's on a per mole basis. The magic has ended, people. I don't know the average atomic mass of tin off the top of my head, so someone's gonna have to help me out on this one. What?
118.7.
What is it?
118.7.
118.7 plus 19 plus 19 gives me 156 point what? 71. Depending on which periodic table you have. Okay. Then moles of tin 2 fluoride, those cancel. Right? Now it's just a math problem. Problem was 1 step. The second problem we did was 2 steps. These are 3 steps. But it's definitely a pattern. guys. Okay? In your packet, page 5 says mass-mass relationships. That's just what we did. We went from the grams of one thing to grams of something else. So here's what I'm going to do. I am going to walk you through another problem. Alright? I don't usually do this, but because our time is short, I'm not going to ask you questions. I will talk and I will tell you what I'm doing, but I won't ask you questions. Okay? Just so we get another example down, so if you want to go back and look at it, you can. Okay? So, why don't we do number 2? Just because the equation is easy to balance. Oh, that's what's wrong with no. Oh, that's a good thing I picked number 2 because something's wrong with it. So, all right. So number 2 on the sheet, it says one reaction used to produce hydrogen gas is the single replacement reaction of magnesium and hydrochloric acid to produce magnesium chloride and hydrogen gas. If you notice, that equation does not produce hydrogen gas. This should not say H2O, it should just say H2. So it says, what mass of hydrochloric acid would be needed to react with 2,000 grams of magnesium? So, first things first, what mass of hydrochloric acid would be needed? That means I have to find grams of hydrochloric acid, right? If it's asking you for what mass, that's asking you for grams. Things I know. I need to react with 2,000 grams of magnesium. So I know that I start with 2,000 grams of magnesium. The other thing that I need to know is a balanced chemical equation. So Mg, shouldn't write it there, over here, Mg plus HCl gives me MgCl2 plus H2. That equation is not balanced as written, but it's pretty easy to balance. Put a 2 out in front like that, go there. Okay? All right, then we start going through and making a plan. Our plan for doing this is a conversion problem. So, we start off with the amount that we were given, 2,000 grams of magnesium. Times sign, fraction bar. Grams of magnesium has to go on the bottom of that conversion factor because we can't compare grams of something to grams of something else. It's got to be moles to moles. So my first step is to convert grams of magnesium into moles of magnesium. In this case, right, when we're converting grams of something to moles of something, this is always on a 1 mole basis, regardless of what the coefficient is in the equation. In this case, it's 1 anyway. Here, this is just an element, right? So I get the average atomic mass, or the molar mass from the periodic table, and it's that number. Mathematically, grams of magnesium would cancel, and units-wise, we'd be left with moles of magnesium, but that's not what we want. So times sign, fraction bar. Moles of magnesium has to go on the bottom of this conversion factor. Moles of HCl on the top. Because we're comparing moles of one part of this reaction to moles of the other part of the reaction, this becomes our mole ratio. Coefficients from the balanced equation go in it. 2 for hydrochloric acid, 1 for magnesium. Moles of magnesium would cancel, and we'd left with moles of HCl, but it's not what we want. So times sign, fraction bar. Moles of HCl has to go on the bottom of this conversion factor to cancel out. And we go grams of HCl on the top. Converting moles of one thing to grams of that same thing. is always on a 1 mole basis, regardless of the fact that there's a 2 coefficient in the equation. That doesn't matter when we're converting moles to grams. Then, formula mass, by adding the average atomic masses of these two things together from the periodic table, and I believe you should get 36 or 36.45, 46, okay? And then moles HCl, and we're left with grams of HCl just like we wanted. You plug that through your calculator, and you get 599.177, alright? And that should probably round to 599.2, as long as Suzanne did the math right in her calculator. She is confident that she did, so. Alright, quiz on Monday. The rest of those problems, the answers are posted online, so you can check those out. I would suggest you do so before your quiz on Monday.